Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Elastic Properties of Composites from the paper Functional Materials. The purpose of this module is to make the students familiar with first, the matrix reinforcement phase interface. Second, the elastic properties of composites, laminates. Third, hybrid and short fiber composites. So let us start with a basic introduction about the module. Composite materials have become essential part of today's life because of many applications and advantages. Recently, there are many researches going on in this field of engineering design and developments to improve the mechanical properties and thermal properties such as stiffness, fatigue, corrosion, resistance, high stiffness to weight ratio, high strength to weight ratio, thermal resistance, etc. Fiber reinforced polymer, usually made of polymer matrix, reinforced by short or continuous fibers. Polymer matrix usually consists of epoxy, vinyl ester or polyester thermosetting plastics because of its excellent properties and the cost of material. Glass, cellulose, aramid, silicon carbide and carbon fibers are commonly used in fiber reinforced polymers. There are several methods to evaluate the mechanical properties of the composite materials such as experimental, analytical and computational methods. Computational modeling and analysis method is developed drastically in these few years. Many models are devised to calculate the elastic properties of composites. Matrix reinforcement phase interface. Since the matrix and reinforcement phase are two different materials, there will always be an interface between the two. Effectiveness of the composite depends on the proper bonding between these phases. Adhesives of additional phases, they are added to enhance the bonding between the two main phases. For example, glass fibers, they are coated to achieve adhesion with thermoset resin. In some cases, the matrix and the second phase may be soluble and form a different kind of bond. Of various kinds between a matrix and the reinforcement. The first figure shows a matrix phase and the blue one is the reinforcing phase, and this dark blue and this light blue is the interface. Now the second figure shows that there is some orange layer formed at the interface which is composed of third ingredient, and this yellow or this orange layer is converted into a blue one composed of the diffused layer of matrix and reinforcing phase. General properties of composites. Now let us look at the general properties of composites. First property is the mass of the composite. Total mass of the composite would be simply the sum of the mass of the matrix, which is represented by mm, and that of the reinforcement phase, represented by mr. So the total mass of the composite, that is mc, is equal to mm plus mr. Next is the volume of the composite would be the sum of the volume of the matrix phase, the reinforcement phase, and a void, if any. If there are no voids, then we can reduce the third term to 0. Hence, Vc, the volume of the composite, is equal to Vm plus Vr plus Vv. The third is the density of the composite. Now we know that the density is nothing but the ratio of mass divided by volume. So the density of the composite, that is rho c, will be mc by Vc. Mc is equal to mm plus mr by Vc. Since mm is equal to rho m multiplied by Vm and mr is equal to rho r multiplied by Vr. From the above relations, we can conclude that the following relation between the density of the composite and its constituent, that is rho c is equal to Fm rho m plus Fr rho r, where Fm is equal to the ratio of Vm by Vc and Fr is the ratio of Vr by Vc. Here M corresponds to the matrix, R corresponds to the reinforcing phase, and C corresponds to the composite. Elastic properties. Now students, let us discuss the elastic properties, and when we are considering the elastic properties of composite, we can consider the two very different model which happens to give us the lower and the upper bound of elastic modulus for the composite. These models are called continuity of strain or isostrain model, which is shown in the figure A, and the second is the continuity of stress or isostress model, which is shown in figure B. Elastic properties according to the Voigt model. When there is a continuity in strain, the model can be treated as a set of spring in a parallel arrangement. It can be easily seen that EC is equal to Fm Em plus Fr Er. It is also termed as the rule of mixture, as the modulus is proportional to the volume fraction of each phase. It gives the upper bound of the modulus of the composite. It is a good approximation for measuring the modulus along the direction of the fibers. Elastic properties according to Voigt model. These are the figures which describes the Voigt model, where the left side figure shows the Voigt and the Rius model, and the right side figure shows the loading along the fibers for the Voigt model. So in this figure, the variation of EC versus the variation of VF have been shown in this figure. Elastic properties according to Riss model. So according to this model, which is nothing but the isostress model, when the configuration of the composite is such that the stress applied on the matrix and the reinforcing phase are same, then it is called as the isostress model. As the name suggests, the stress is expected to be uniform across the various phases. This model is also called as the Riss model and gives us the lower bound on the modulus of composite. Actual value would most likely be higher than that calculated using this model. So one can clearly see that EC prime is equal to EM ER divided by FM ER plus FR EM. This model is appropriate when the stress is being applied perpendicular to the direction of the orientation of fibers. Effect of fiber orientation. Now the above point brings us to an interesting stage, that the orientation of the applied stress with respect to the fibers, assuming they are unilaterally oriented, has a great influence on the overall elastic modulus of the composite. This has been experimentally verified, and one of the results is given in this figure, where it shows the variation of the elastic modulus versus the orientation of the fiber or the fiber angle in degrees. Real composites. As mentioned earlier, real composite materials would show behavior which would lie between the two extreme models discussed. In real materials, nu-F and nu-M would not be the same, and that will also affect the overall elastic behavior. When nu-F is not equal to nu-M, then E11 is approximately equal to EF nu-F plus EM multiplied by 1 minus nu-F. Along E22 direction, the modulus depends on the contiguity of fibers, and this is incorporated by introducing a factor C. So E22 will be equal to E reus plus C multiplied by E void minus E reus, where C is equal to 0 for completely isolated fibers and 1 for fibers in contact. Elastic properties of laminates. Laminar composite structures are formed by laminates which are usually composed of unidirectional fibers. These laminates can be arranged in various ways. So these are the figures which shows the various possible orientation for laminates. So they can be arranged in only two primary direction, or they can be arranged so as to give the random average orientation to fibers or something in between. So in order to understand the properties of laminate, we need to look into the elastic property of a single ply laminate, that we will discuss later on. Elastic properties of single ply laminate. Now we can assume a unidirectional laminate which has one major axis of anisotropy in that it coincides with fiber directions. Let us assume it to be in 1-1 as in E11 direction. Stress-strain relation for the orthotropic plate can be given by the tensor of epsilon 11, epsilon 22, epsilon 33 is equal to the 3 cross 3 matrix, where the first element is 1 by E11 minus nu12 divided by E11, 0, minus nu12 divided by E11, 1 by E22, 0, 0, 0, 1 by 2 G12, and this matrix multiplied by the matrix of sigma 11, sigma 22, sigma 33, where minus nu12 by E11 is equal to minus 21 divided by E22. So continuing our discussion over the elastic property of single ply laminate, if the unidirectional ply is stressed at some angle theta, then the elastic modulus E theta, shear modulus G theta, and Poisson's ratio nu theta along these directions can be given by 1 by E theta is equal to cos to the power 4 theta divided by E11 plus sine theta to the power of 4 divided by E22 plus bracket 1 by G12 minus 2 nu12 divided by E11 bracket close sine square theta cos square theta. The second equation for G theta is 1 by G theta is equal to bracket 1 by E11 plus 1 by E22 plus 2 nu12 divided by E11 minus 1 by 2 G12 bracket close, this whole multiplied by sine square theta cos square theta plus 1 by G12 multiplied by bracket sine theta to the power of 4 plus cos theta to the power of 4. The next equation for nu theta is nu theta is equal to E theta multiplied by bracket nu12 divided by E11 bracket sine theta to the power of 4 plus cos theta to the power of 4 bracket close minus 1 by E11 plus 1 by E22 minus 1 by G12 multiplied by sine square theta cos square theta, the whole bracket close. Now students, let us discuss about the elastic properties of multiply laminates. Once we have the elastic properties of single ply laminates, elastic properties of randomly oriented multiply laminates can be given as the average of various oriented single ply laminates, that is average of E is equal to integral 0 to pi by 2 E theta d theta divided by integral 0 to pi by 2 over d theta. An approximate solution for the above equation is given as average of E is equal to 3 by 8 E at 0 degree plus 1 by 4 E at 90 degree, and the average of G is equal to 1 by 8 E at 0 degree plus 1 by 4 E at 90 degree. If the laminates are in orthogonal direction, a simple form of the equation is average of E ortho is equal to E11 VF 0 degree plus E22 VF 90 degree. Elastic properties of multiply laminate. Now, in the above equations, E11 and E22 can be obtained from single ply laminates using void and Reus models. So, this figure depicts the effect of randomizing the fiber orientation on the composite modulus. So, this figure depicts the effect of or the variation of the fiber orientation on the composite modulus as a fraction of E11. Elastic properties of multiply laminates. Another simplified model to calculate the elastic modulus of multiply laminates utilizes the efficiency factor, that is eta, which considers the contributions of groups of parallel fibers in the plane of laminate. This model assumes nu f to be approximately equal to nu m and that the fibers are long enough to ignore the end effects. Here eta is equal to the summation of an cos theta to the power of 4, where an is the proportion of fibers at angle theta. It can be seen that eta is equal to 1 for unidirectional laminate, while for 0/90 cross piled laminate, eta is equal to 0.5 and so on. Hence, EC is equal to eta EF VF plus EM VM. So now students, let us discuss about the hybrid composites. Hybrid composites are a variety of composites where the structures of different kinds are mixed together. Structures, they can be different at microstructural level or a laminate level. Hybridization allows the composites to enhance the beneficial properties of the various laminates while subduing the deleterious effects on the overall properties. So, the elastic properties of such hybrid composites can be predicted using the mechanics which we have discussed earlier, using the mixture rule, that is E is equal to the summation over I is equal to 1 to n EI multiplied by VI. Hybrid composites. Flexural modulus of such hybrid composites can be obtained by E hybrid is equal to 1 by 3t multiplied by summation over I equal to 1 to k bracket z I plus 1 to the power of 3 minus zi to the power of 3 bracket close the whole multiplied by EI, where T is the laminate thickness, Zi is the distance to the bottom of the ith ply, and Zi plus 1 is the distance to the top of the ith ply. EI is the flexural modulus of ith ply. Now let us discuss the elastic properties of short fiber composites. When fibers are short in length as shown in this figure, then the mechanics of load transfer changes. Stress cannot be applied directly to the fibers and must be transferred by shear force through the interface. This also implies that a good bonding must exist between the fibers and the matrix. A simple model to understand that is that the load transfer starts to build up from the ends and can reach a maximum stress or fracture stress of the fiber. This implies that only the middle part of the fiber where the load is saturated is effective in reinforcing the matrix as shown in this figure. The below figure shows the variation of the fiber tensile stress and interface shear stress along the length of the fiber. Continuing our discussion over the elastic properties of short fiber composites, modulus E11 for such short fiber composites, assuming that all the fibers are aligned and can be given by E11 is equal to Em multiplied by bracket 1 minus Vf bracket close, or nu f plus Em nu f eta, where eta is equal to 1 minus tan hyperbolic of beta L by 2 divided by beta L by 2, and beta is equal to the square root of 2 gm divided by Ef r square log to the base E of capital R by small r, where small r is the fiber radius and 2r is the approximate interfiber spacing and L is the length of the fiber. It is obvious from the above equation that as the length of the fiber becomes large, eta tends to 1, and hence we get back to the usual rule of mixture. So students, let us summarize what we have learnt in this module. First, the phenomenon of the interface which is formed between the matrix and reinforcement phase has been explained in detail. Second, the mechanical models for relating the elastic properties, that is isostrain model and isostress models, they have been discussed. Third, the elastic properties of single and multiply laminates are also discussed. Hybrid and short fiber composites were also discussed in this module. Thank you.